and welcome to Chapter 12. In Chapter 12, we're going to talk about a concept called recursion. Recursion can sometimes be a little difficult to visualize because it's a pretty abstract concept, but it's actually one of the more powerful functions that we have in programming. It's the ability for a program to call itself. Let's get started. So as I said, recursion is about programs being able to call themselves. They refer to themselves in the program. So if you've ever done an algorithm or a thought, of how to do something, and it involved taking a concept and breaking it down and doing smaller projects. So if I wanted to do 10 of something, well, I'm going to do 1, and then I'm going to do 9 of the exact same thing. Then I'm going to do 8, and then I'm going to do 7, then I'm going to do 6. So I'm going to keep breaking them down. If I'm going to take a deck of cards and I want to separate them out, I can break it in half, and then I can break it in half again, and then I can break it in half again, and then eventually I'm going to sort my cards, and then I can put it all back together. So breaking a project down into smaller pieces is really what recursion is about. A lot of times those smaller pieces follow the exact same rules as the whole project as a whole. It just would be really hard to do it that way. So doing things where you break your problem into smaller parts and then be able to access that from itself and call itself, because we want to do exactly the same thing, is what we do in recursion. The important parts about recursion are including a base case, or a case that doesn't need recursion to solve it. So if I wanted to solve a problem between, if I had 2 cards and I wanted to know which one was the larger of the 2 cards, I don't need recursion to solve that. I can just look at the 2 cards and move on. So that would be called your base case when you're down to just the last 2 cards. But if you wanted to sort your entire deck of 52 cards, you could break it down into 26 cards, then break it down into 13 cards, then break it down into 7 cards, then break it down into 4 cards, then break it down into 2 cards, and finally look at the 2 cards and go, which one of these 2 goes first? Cool. Now go back and do that to the rest of the deck, the other pieces that I've broken down. That quit condition, that base condition, is really, really important when you're using recursion, because in recursion, we're going to be calling ourselves, and we need to know at what point do we not call ourselves. If you don't have a base case, if you don't have a quit condition, your recursive code will just call itself indefinitely until the code breaks. So on the example I've given you here, it says previous line was repeated 991 times and we hit the maximum recursion depth. Recursion depth in Python, actually recursion depth in general, refers to how many times you've called yourself. If you call yourself indefinitely, you will crash your computer because you'll just keep going. You'll use up all the memory and it'll just die. So Python likes to put in a break where it says you can only recurse 1,000 times. After that, this is getting silly. We're going to come back out. And it's just kind of a fail-safe that we throw into Python to make sure that you don't end up using up all your memory and crashing your computer. So after 1,000 times, it says, okay, I'm done. This is it. We're good. You can change that, by the way. If you need to do recursion more than 1,000 times, you can, but you just have to tell the compiler that this is what you want to do. In the example that I have here, I have my main function. So I'm going to call main, and main is going to call a function called message. And message is going to be a function that says hello world and then calls message again. So you can envision that I'm going to print hello world and then I'm going to call message. And I'm going to go in there, I'm going to print hello world, I'm going to call message. There is no base case here. There is no termination case in this code, which is why it crashed, why we got that stack flow error on it. And so this is the basic concept of recursion, but you never want to write your code this way. You always want to include a base case, which we'll talk about in the next slide. So that base case completes the function without calling the recursion. So we sometimes like to create our recursive function as an if-then statement. If we're in our base case, then do whatever we have to do with our base case. Otherwise, go ahead and do your recursive case. So we split this into 2 cases. It's kind of the if-else case, but in this case, it's the base case and the recursive case. So the base case is the one that does not call itself. And we usually put that first because as the programmer, we want to make sure that we hit that base case. We want to make sure that that's the first thing we found. And in the off chance that whatever our control was came after that, so if I said where number of repeat is not equal to 0, And if we start at 1 and increment, we'll never hit 0. So we kind of want to make sure that we're checking that base case early. Really an important part. So our base case in this case is where we have, I want to repeat my message 5 times. It's similar to a loop, yes, but it's a little bit different in the way that it's coded and the way that it's programmed. You don't have to do anything special with a recursive function to tell Python that it's recursive. It can figure it out. In other languages, you might use a recursive keyword, or you might use some other type of notation to show that it is a recursive case. But in this case, you just do a function the way you normally would, and you just call your function from inside your function. So in this case, I have said, if my number of repeat is equal to 0, then I'm going to print done, and I'm done. Otherwise, print which repeat I'm on, and then call message again with the number of repeat -1. The -1 is really important. You have to shrink the size of your problem every time you go through recursion. If you increase the size, or if you keep the size the same, it doesn't ever get solved. So the point of recursion is to break problems into smaller parts. In this case, I am going to call message 5 - 1, or 4 times, the next time I call it. And then I'm going to call it 3 times, then I'm going to call it 2 times, then 1 more time, then I'm done. So you can see that I'm going to print what my number repeat is, and then my message I'm going to go ahead and call again. When I run it, all I'm going to get is it running the recursive message, the function 5 times, well 6 times, because it'll go from 5 to 0. The 5 times it'll print out, so it'll print out each of those first 5 times, and then when it gets to that 6th time, where my number repeat has now decreased from 5, 4, 3, 2, 1, now it's 0. Now I hit my base case, and now I can say done and break out of it. So this is called tail recursion, because the last thing that's done in the code is the call. Sometimes if you want to break out of code, if you want to use a break, if number of repeat is equal to 0, then break. You can do something along those lines, but it's better to keep it kind of without using the break as much as possible. Tail recursion just means the last thing in my code, in my function, is going to be that recursive call. There is no code that comes after that. You can add code that falls after you've called your message. What'll happen is your code will go into your function. In this case, it'll print number of repeat is this. Then it'll print your message, which means it'll go back and it'll run the code again. And then when it's done and it's finished and it's coming back out, then it will run the code after the call. That is not tail recursive. Tail recursive is where the last thing you do is the recursive call. Tail recursive is more efficient, so we like that a little bit better, but sometimes you like to do things after you break out of your recursion. So yeah, I'm out now. I'm back into this function. I'm back into that function. The concept with recursion is that you're creating kind of multiple versions of the function, and you're calling each of them with their own set of parameters as you go along. You might have 5 or 10 or 20 of these, and that's fine. You're going to go into that with its set of parameters, answer it, and then come back out the way you would with any other function. Recursion is a way to loop without a loop. And each time you have to decrease the complexity. The complexity part has to be decreased. Again, if you never do a number repeat -1, or you never break down, do half of my sentence, then a third of my sentence, or then a quarter of my sentence, and break it down each time, your problem will never get smaller, and the recursion will go on forever. So the point is to end up with a smaller and smaller case until you get to your base case. To be fair, any problem can be solved without recursion. You never have to use recursion. It is not required to solve a problem. That being said, there are some problems that are much easier to understand by breaking them down into smaller and smaller problems and then calling that problem again. So is it easier to sort 3 cards than it is to sort 300 cards? Well, yeah, it's a lot easier to sort 3 cards than it is to sort 300 cards. So a smaller version of the problem is easier to solve, and it's easier to visualize for you as a programmer. The important thing when you are solving a problem with recursion is to recognize you have to have a base case and a recursive case. I've said this a few times, but I need it drilled into your head. Those are the important parts about recursion. If you forget to add your base case and you just do the recursive case, you will never finish your problem and it'll go on forever and ever. So your base case is, if the problem can be solved now without recursion, then have the function solve it and move on. So go ahead and return whatever value you need to return and be done. In the recursive case, the function reduces the problem into a smaller, similar problem then calls itself with that smaller problem. So if I had, again with the cards, if I had a deck of 50 cards, I could take the deck, split it in half, and then call the recursion on the 25 cards twice. So I could call sort this set, and then combine the two sets together. Each iteration of your recursion should get the problem closer to the base case. So you call recursive case, recursive case, recursive case, and then finally base case. And it should do it in that order, where you're doing recursion a few times and then you hit the base case, then you come out of it. So you should get closer to that base case. The base case doesn't use recursion, so it doesn't call itself. So that's a kind of stopping point so that we can move forward from there. So let's give you a couple of examples on what we mean by recursion. So if you remember your high school math classes, there's a concept called factorial, which is just all of the numbers from number n down multiplied by each other, except 0, because if we multiplied by 0, the whole thing would be 0. But down to 1. So we're going to assume at the beginning, when we do our factorial, that if 5 factorial is 5 times 4 times 3 times 2 times 1. So all of these numbers multiplied together. We're going to start with our first number and multiply it by the factorials of those one less. So we're going to assume first off that 0 factorial is just 1, because if it wasn't, then we'd be multiplying by 0 and everything would get confused. So 5 factorial is actually 5 times 4 factorial. Well, that's kind of cool. Let's go find out what 4 factorial is. 4 times 3 factorial. 3 factorial is 3 times 2 factorial, so on and so forth down to the bottom until you get to 0. So our algorithm for factorial with recursion is, if my number is 0, then return 1, because that's my base case. So when I get down to 0, I just want to return 1. I don't have to multiply anything. I don't have to call recursion on it. I don't have to call factorial on it again. I can just say the base case is when n is equal to 1. Any other case, I am going to return the number itself, 5, 4, 3, 2, 1, whichever one it is, times the factorial of the number less than it. So n minus 1. We're going to decrease by 1. So when I'm doing factorial of 1, I'm going to return 1 times factorial of 0. Factorial of 0 was 1. We already set that as our base case. In this case, when we do factorial of 5, it's going to take 5 times the factorial of 4, factorial of 3, factorial of 2, factorial of 1, factorial of 0, and then it'll come back up and get you your 120. So a really simple way of looking at how to multiply numbers together. We just have to decrease it each time and just multiply them. You could do the same thing with summation, adding them together. So this is just a really simple example of how we would use recursion, what the code looks like, and how to get the answer. There are 2 different types of recursion. Most recursion you do is going to be direct recursion, which is where the function calls itself. My function calls my function inside of it. So each of the functions calls themselves individually. And that's direct recursion. You are directly calling yourself. You can have the concept of indirect recursion, which can sometimes lead to a circular reference. So you have to be careful about this. This is where the function calls another function, and then that function calls the first function again. So if you think about it, if I have function A and function A calls function B calls function A, which calls function B, which calls function A, which calls function B. You have to make sure you are decreasing your complexity each time if you're going to do it this way. If you don't decrease your complexity, you're just going to go around in a circle forever and ever. So indirect recursion is where somebody else calls you, but you called that person first. So kind of doing those 3-way phone calls. So we're going to call this person, then this one, who's going to call back to you. And then we're just going to go around in a circle. So direct recursion is what most of the stuff that you're going to be doing is. So at least at the beginning of your programming career, but if you want to keep moving on, you may end up with some indirect recursion as time goes on. All right, our second example is a concept called Fibonacci. So the Fibonacci series is a mathematical series that we use actually in nature. In nature, it shows up automatically in a lot of situations. The insides of a shell or sometimes the leaf of a tree can follow this kind of recursive, natural forming list of numbers. The Fibonacci series itself is 0, 1, 1, 2, 3, 5, 8, 13, 21, 24. The way that they came up with the series was that they used what we call Pascal's triangle to create it. And Pascal's triangle starts with a 1, and then the outside numbers are always 1s, and the inside number between the two numbers is always the addition of those two numbers. So 1, 1, 1, 1, 2, 1, because the number in the middle would be 2, and then 1 plus 2 is 3, so 1, 3, 3, 1. You use this in a lot of things in mathematics. We use it for polynomials a lot to determine what two numbers to a certain power is, things like that. But it's a big mathematical number. The question that gets asked often is, at the 7th index, what is the Fibonacci number at that index? Well, how would I find out that the 7th number is 0, 1, 2, 3, 4, 5, 6, 7, was 13? How do I know that? Like, do I have to go through all of the math to do it? Well, yeah, you kind of do. But can I have the computer do the math for me so I don't have to figure it out? And yes, you can. You can use recursion. The thing you want to be careful with Fibonacci is that once you get past larger numbers, anything higher than 20 or 25, the numbers start to get really, really huge. And your computer probably will crash somewhere between 30 and 40, somewhere in there. The concept of being able to come up with the next number is that you have 0 and 1, and you always start with 0 and 1. So my base case is 0 and 1. 0 and 1 return either 0 or 1, because those are the first two positions. So the 0 index is 0, first index is 1. So I can make those two my base cases. So I have a 0 and a 1 base case. If I have the second index is going to be 0 plus 1, or the 0th index plus the first index. In this case, I can run a recursion with Fibonacci to say, return Fibonacci of n minus 2 plus the Fibonacci of n minus 1, or essentially the index that's 2 away and the index that's 1 away from the index I'm looking at. So my second index is going to be index 0 and index 1. Both index 0 and index 1 are base cases. They both return numbers, and I have my answer. It's 1. When I do my third index, now I'm going to say, what is the Fibonacci for 3? And I want to get the Fibonacci for 2 and the Fibonacci for 1. Well, the Fibonacci for 2, which we just solved, was 1. So we're going to go and do this multiple times. As you can see, each iteration of this increases the complexity a little bit of what's going on in the background, because you're calling yourself multiple times. But it also gets the answer really cleanly and easily. Like, we understand it in the sense of, we know that the way to get the third index is to take the second index and the first index and add them together. We know that to get the 10th index, we take the 9th and the 8th index and add them together. Well, how do we know what the 9th and the 8th index are without coming up with the whole list? We have the program do it for us using recursion. So in this case, I could say, what is the position at 10? And I could say Fibonacci of 10. And it'll go through using recursion to solve this, and it'll give me my position of 55, or my number of 55. I can do the same thing to ask for the number at 30. So the 30th index, remember, this is increasing really rapidly. My 30th index is 832,040. So it's a really big number by the time you get to the 30th index. Imagine where you are at the 50th index. That's why it's going to start to crash your computer, because we're going to have to start reducing each time. So to do the 30th index, I have to go find the 29th index. To find the 29th index, I need the 28th and the 27th. To find the 28th, I need the 27th and 26th. And you're calling yourself a whole lot of times. There is a way of doing recursion in this type of a problem using a concept called memoization, where we are storing the values that we get at each time. So we can store a list of Fibonacci values as we go. And in that case, all you have to do is go get the value from the list rather than having to recalculate it each time. And that increases your efficiency rapidly. You could actually do the Fibonacci at 100 and you'd be fine. But so this is a basic concept. We again have our base case of our 0 and 1 that returns something without using recursion, and then all the rest of our cases which use recursion, making sure to decrease the complexity of our problem each time we go into them. Another example. It's always good with recursion to give examples, because one of these I hope is going to click in your head and you're going to go, oh, I get it. I get how that's done. When you do fractions, I know you're having a little panic attack about fractions. Some people really didn't like fractions. I loved fractions. I thought they were fabulous. But when you're adding fractions, you have to find the greatest common divisor. So GCD. There was the other one that's the least common multiple. People usually got those confused. So the greatest common divisor is the largest number that is a divisor of the number that you're looking at, of both numbers that you're working with. So I have two fractions, one of which is, something over 48, and one is over 136. And I need to know what number divides evenly into both of them. Something along those lines. So we need to find the greatest common divisor. In this case, How do we do that? Well, the way you do it in math when you were first taught is you take all of the divisors of 48. So 48 can be divided by a 2, a 3, a 4, a 6, an 8, a 12, a 24, and a 48. All of these numbers go into 48 nicely and come out with a remainder of 0. So you're going to remember that remainder term because when we explain the algorithm. So the remainder of all of these is 0. 136, the divisors are 2, 4, 8, 17, 34, 68, and 136. So you go through and you figure out what all the divisors are. But if you remember back to why people hated fractions, how do I know which numbers I'm supposed to pick? So I can pick 2 and 3 and 4. Those are pretty easy. Then I look at 5 and I go 5 doesn't work. Then I go 6. Okay, so sometimes 6 works. Let's see, 7, 8. Okay, 8 worked. 9, 10, and then you start guessing and then you're just frustrated. I usually, by the way, did factorization at this point and then I'll do it that way. But the point is, how do you figure it out? The algorithm using recursion in mathematics is if you have two numbers and you always make your x your larger of the two, so it's really important that you do have the larger number first. If your x is evenly divisible by your y, then the greatest common divisor of the two is y, because obviously there's no numbers larger than y, so you can't go any greater than y. And if y goes into x nicely, then we know that it's a divisor of x and we're good. So we found out if x goes in, or if y goes into both x and y, then we know that's the greatest common divisor. So that's our base case. So we can think of it as our base case is when x is evenly divisible by y. How do we know if it's evenly divisible? We use that modulus, and we make sure that the modulus is equal to 0. So modulus says, what is the remainder of two numbers? X modulus y is going to give you 0. That's my base case. Cool. I can do that without having to do any recursion. So if my x modulus y is equal to 0, then just return y. That's my greatest common divisor and move on. Otherwise, what we do is we find out what the greatest common divisor is between y and the remainder between x divided by y. It seems a little weird if you haven't ever done greatest common divisor this way, but it's a really fast way to find your greatest common divisor. So if I had 136 and 48, 136 modulus 48 actually returns 40, so it doesn't go in nicely. So I'm going to go find the greatest common divisor between 48, which was my y, and 40, which was my remainder from the division. So I'm the 136 divided by 48. Okay, so I have 48 and 40. So 48 and 40. 48 and 40 don't go into each other nicely because there's a remainder of 8. Okay, cool. Then I want to find the greatest common divisor between 40, which was my y in this case, and 8, which was my remainder. Cool, let's go find the greatest common divisor between 40 and 8. Oh wait, that goes in nicely because 8 times 5 is 40. So I can just return 8. Each of these returns 8 all the way up, and the greatest common divisor was 8. As you can see from the example that I gave above with the highlighting to show you that 8 was the answer. So being able to do this, it only took 3 steps, 4 steps to be able to get the answer, instead of having to calculate out what are all of my divisors and what are all of my divisors. Again, any problem that gets solved with recursion can be done with looping. You could go find all the divisors of 48, go find all the divisors of 36, put them both into lists, then go through both of the lists and figure out where the largest number is that they match. You can do that, and that's okay. It just takes more complication and more time. If you understand this algorithm, it's so much faster. So this is how you do greatest common divisor using recursion. As you can see, I did 256 and 112. The greatest common divisor between those two, you might go, okay, I know that a 2 works. I can do that 4 thing, and I know a 4 works in there too. Does an 8 work? What about 6? What about, and then you start guessing. This one was 16. Would 16 have been one of the first ones you would have checked? So being able to use the program to figure out your greatest common divisors is kind of useful. We can't do a recursion lesson without explaining Towers of Hanoi. So Towers of Hanoi is like the programming conversation about recursion. We always bring this one up. Towers of Hanoi is a mathematical game. And it's in your book, and it's going to be the one that you're going to do on your own. They have written the code for it for you, but I do want you to spend some time going and looking at it. It uses 3 pegs and a set of discs. The original set of discs was 64 discs, but you're going to start with 3. And you're going to say, how can I get all of the discs from the first peg to the third peg, following the basic rules, which is you can only move 1 disc at a time. A disc cannot be placed on top of a smaller disc, And all of the discs must be on a peg unless they're currently being moved. So you can't hold a disc in your hand and then move the next one. So if you have 3 discs, how do you move all 3 of them to another peg? Well, the 3 is kind of the easy one. You take the first one off, you put it on the second peg. Take the second one off, you put it on the third peg. Then we take the first one off the second peg and put it on the third peg. Then we take the third one off and put it on the second peg. Then we go back and then we end up taking the first one off, putting it back on the first peg, second peg onto the third peg, the third peg onto the second peg, and then the first disc back on top. The point is, how do you move them all? Take a little bit of time. Give yourself 10, 15, 20 minutes to read this problem, do the coding. Understand the algorithm, because the algorithm is actually kind of cool. How do you move these when you can't ever put a smaller disk on top of a larger disk, or on top of a larger disk on top of a smaller disk? How do you move it? Code the program. Make sure you follow the book and do the recursive part of the program. There is a way to do it with loops. I don't recommend it. It's very, very long and complicated. Do it with recursion. It's nice and simple and easy. So go spend some time doing this and then come on back when you're done. Hopefully that Towers of Hanoi was kind of fun and you played around a little bit and got to understand how it was done. So I've said a couple of times, every recursive problem can be solved with looping. So why? Recursion is actually less efficient, where it uses more memory and it takes a little bit more processing power to run it. So why would anybody ever use recursion? It depends on how you see the problem. And it's all about you. It's all about your way of coding. If you can see the problem as a problem that can be broken down into smaller parts that are exactly the same problem, just smaller, then recursion might be the better way to solve the problem, because being able to break it down into smaller parts makes the code easier to understand. The thing with easier to understand code, it's easier to do it right and to not make as many mistakes. You want to try to avoid mistakes as much as possible. If your code gets hyper complex, you can start causing errors without even trying, because there's just so much stuff going on in your code. Recursion is nice and simple and easy. It's just, let's break it down, do a smaller problem, but the base case stays the same. Don't forget that base case. You could do the greatest common divisors with loops, sure. But wasn't the recursive answer a lot easier? So this is back to you personally as a programmer when you want to use recursion. And sometimes it's obvious. If I see the problem as something that can be broken down doing the smaller versions of the problem, recursion might be the way to go. If I can't, don't fight it. Don't force it, except for in your homework. But recursion isn't required. You never have to use recursion. It's just a tool that you want to use if you can, because it does make things easier. All right, there are 3 sets of homework, not 3 problems, 3 sets. The first set of homework is doing the 3 problems from the textbook. So it's 2, 3, and 6. There is no quiz this week. So I didn't want to do a quiz on recursion because I felt like it's more of a programming type problem than a semantic trying to figure out words problem. So there's no homework or no quiz for this week. 2, 3, and 6 from the textbook. Yes, you have to use recursion to solve these problems. All 3 of them are designed for recursion. That's why they're in the textbook. But you have to do 2, 3, and 6 from the textbook to do and use recursion in all 3 of them. Homework 2 is kind of a generic problem that I came up with. When you go to a store, sometimes you get a buy 2, get 1 free. If you have X amount of money and each item that you want to buy costs Y, and you get 2 items, for every 2 items that you buy, you get 1 free. Build a recursive program to figure out how many items you end up getting for X amount of money. So if something costs $10 and you have $40, okay, I can buy 2 and I can get 1 free. So I buy 2 of those at $10 each, that's $20, and I get 1 free. So that means I end up with 3. Then I can buy 2 more with $20 and I can get 1 free. So I'll get a total of 6. Do this for larger amounts. So if I have $300, how many items do I get without having to count them up individually? Use recursion, break it down into multiple problems. When you have finished that one, so hopefully that doesn't take you too obnoxiously long to program, but I want you to really think about how do you break it down into smaller problems and how do you call it on itself to figure out what do you have left. I want you to do it where the user can enter buy X or buy M and get N free. So buy 3, get 2 free. Buy 6 and get 1 free. Buy 5 and get 4 free. Change it around. Figure out if you can change that by adding parameters to your function and being able to still do it recursively. I want both projects. So don't take the first project and alter it to make the second part of this. I want both of them. So you can copy and say this was the first one and then we're going to change it. But I do want both projects to be returned because I want to see that you did the first one first and then did the buy M, get N free. And your last one. So there's only three. Well, five, depending on how you look at it. I want you to create a triangle of summations. Now, this is not Pascal's triangle. This is, you're going to enter a list of numbers. So whether you have the user enter a list or whether you're starting with a list, I want you to start with a list of numbers, at least 5 or 6, because it needs to be a large amount of numbers. And then you're going to create a triangle from that list and print it out. The printed out part is interesting because you might print your triangle upside down, and you got to be careful about that. So if I were given the input of 2, 4, 5, 7, 9, the next row up from that should be 2 plus 4 is 6, 4 plus 5 is 9, 5 plus 7 is 12, and 7 plus 9 is 16. So that's my next one. Then that one, I want to do the next one up from that. So I'm going to do 6 plus 9 is 15, and so on and so forth, until I get to a single number in my list. That's your base case. So your base case will be having a singular number. Be sure to print your list during each iteration. You can include lists. You can have code before and after your recursive function. So figure out where you want to print that. Go ahead and add in some print statements while you're coding to make sure you understand it. And I want the output to look similar to this. Now, yes, this is a right-sided triangle as opposed to a right-angled triangle instead of a normal isosceles triangle, but that's because I didn't want to make the effort of printing it weird. So this is the triangle that I want you to create. Go ahead and test it with these numbers and make sure that you get them right. Make sure you do your math right. And try to have some fun with this. So make sure it can handle a list of 10 numbers and it'll print 10 rows of summations. Okay? So have some fun. Do well. Give me a call if you need anything, and have a fabulous week.